In this video, I will derive and discuss the range equation. Let's consider an object that is projected into the air with some initial velocity v0 and at an angle theta above the horizontal. When the object returns to the ground, we can measure the horizontal distance traveled, and this is referred to as the range. Today we will consider the specific case in which the ground is horizontal, so the final height of the object when it makes contact with the ground is exactly equal to the initial height. We will use capital R to refer to the range for this particular case. Now we will derive an equation for the range R that depends only upon the initial conditions v0 and theta. Remember that whenever we have projectile motion, we may consider the motion to be a combination of horizontal and vertical motion. Let's make two columns that contain the information we have for horizontal and vertical directions. For projectile motion, we always know that the acceleration in the x direction is 0, while the acceleration in the y direction is negative 9.8 meters per second squared. I'm calling the y acceleration negative g, indicating that I have chosen down as the negative direction. How about initial velocities? Well, first we need to resolve the velocity vector into horizontal and vertical components, and then those results can be transferred into the columns. Delta x will be equal to r, and delta y is equal to 0 since the projectile returns to its original height. Finally, we don't know the time, but whatever it is, the time it takes for the motion in the horizontal and vertical directions is the same, and so these times are the same. Okay, now we are ready to choose some equations. Let's first consider what's happening in the horizontal direction. Beginning with this equation, which is one of the constant acceleration equations, we see immediately that the acceleration term is 0 since the acceleration in the horizontal direction is 0. Substituting r for delta x and v0 cosine theta for v0x, we have a relatively simple equation. I started out by saying that I wanted to derive an equation for r in terms of v0 and theta, and you can see that I'm pretty close. The trouble is the equation still contains t. Let's see what we can do about that. Moving over to the vertical column, let's use the same constant acceleration equation, but this time dressed up for the vertical direction. Substituting for delta y, v0y, and ay, we get this. We may divide a t out of the equation and then solve for t to get this. Now we have an alternate expression for t that involves v0 and theta, so we'll make a substitution into this equation, and the result is this equation. In a sense, we're done. We have an equation for r that involves only v0 and theta, and that was the goal. But there's one last trig substitution that we can make to simplify the equation a bit more. Perhaps you can see it. Sine of 2 theta is equal to 2 sine theta cosine theta. And so when we make that substitution, we get this resulting equation that's very nice and simple. And this is the equation that you might find very useful to remember. Now that we have the range equation, let's take a closer look at how it works. I'm about to show you a simulation in which I will set the initial velocity of a projectile to 50 meters per second, and then I will fire it at a variety of angles to see how far it goes. I have the option to change the velocity and mass of the object, but I'm not going to do that right now. Take a moment to look at the range equation and see if you can make some predictions about how the range will be affected by the angle. You might even like to pause the movie now while you think about this. To begin with, I will launch the projectile at an angle of 90 degrees, in other words, straight up. And then I'll change the angle to 75 degrees. I'm going to continue reducing the angle by 15 degrees each time, so here's 60 degrees. Now let's see what 45 degrees looks like. You can see that as the angle is reduced, the range is increasing. Will that behavior continue? When the angle is changed to 30 degrees, you can see that actually the range starts decreasing again, and it looks like it's about the same as the range for 60 degrees. 15 degrees, ends up looking like it has about the same range as 75 degrees. Take a moment to see if you can use the range equation to convince yourself that the results you just saw make sense based on the equation. Again, you might even want to pause the video to think about this. Now let's take a look at the graph of sine of 2 theta. The behavior of this function is the key to the range equation because the initial velocity and g were held fixed throughout the last simulation. We were interested in values of theta from 0 to 90 degrees. 90 degrees is here, which means that 45 degrees is right here. Notice from the symmetry of the graph that angles that add to 90 degrees have the same y value. This explains why we saw the same range for complementary angles. Notice also that this graph peaks out at 45 degrees, so this is the angle that will yield the maximum range. I want to end with a final thought. The range equation is wonderful, and students often like it so much that they try to apply the range equation in every situation, even when it isn't appropriate to do so. Let's take a look at a new situation in which a box has been placed in the path of the projectile. Let's launch the projectile again to see if the range equation may still be applied. As you can see, the projectile does not go as far this time. Therefore, it is not appropriate to use the range equation. Remember, we derived this equation by assuming that the projectile returned to its same initial height. Use the range equation only when this holds true. So, what should you do when you can't use the range equation? Well, go back to the beginning of the derivation and replace y with whatever the final height is and solve. You might even want to try this right now.